Here in this video, we would like to consider a problem to explain a concept, right? Let me tell you first of all what's our problem is. Imagine a magnet like this. Let the upper one is the North Pole, lower one is the South Pole, each of poles to the M. Let us consider a line that is equatorial line to this bar magnet. At a point P, who is at a distance d1, I want to find out resultant magnetic induction. But one thing that I want to tell you is it is not just one magnet that I am taking in this problem. I want to take another magnet. This is also assumed like an identical magnet. And this point is again on the equatorial line of this magnet. Let that is at a distance d2 from the center of the magnet. Now, at this point, I want magnetic induction due to both these magnets. I assume magnets are identical in nature. Therefore, the magnetic moments is also same. Right? Let us start solving the problem. That's the problem. You got the problem. Yeah. Now, on this point, due to this North Pole, as I want magnetic induction, I shall imagine a unit North Pole. So, on this unit North Pole, this North Pole applies a repulsion. Along the line of action, resultant force is there. F North due to the first magnet. Again, on that unit North Pole, due to this other pole that is South Pole, there is force of attraction because opposite poles. That is in this direction. This is F south due to the first magnet. These two are equal forces because this distance and this distance are same. So the forces are same. So the resultant will be exactly in between them. Where is the resultant? This way. The resultant of the two forces is called equatorial force due to the first magnet. You know the formula for that B equatorial. We have already derived that formula. What is that B equatorial is? For a short magnet, mu naught by 4 pi m by d1 cube because I have assumed the distance as d1. Let us repeat this for the second magnet. Let us draw the directions. This is our second magnet's north pole. On this north pole, force of repulsion. So what's the direction of that force? This way. This is force due to the north pole of the second bar magnet. On that unit north pole, due to this south pole, there is an attraction. South pole attracts this north pole. This is force south pole due to the second magnet. These two are also equal in magnitude, having some angle. The resultant will be exactly in between them, in line with the first magnet because both are identical magnets. This is B equatorial 2. How much is that? Is the same of the first because both the magnets are identical in nature. And have you noticed this B equatorial and this B equatorial are along the same line? So what is the B total is? B equatorial of the first plus B equatorial of the second because both of them are acting in the same direction. Angle between those two vectors is 0. That is mu naught by 4 pi m by d1 cube plus mu naught by 4 pi m by d2 cube. Of course, if the distances are same, I can write a formula. If, of course, I'm just putting a further condition. If d1 equal to d2, I can find that value as 2 times of mu naught by 4 pi m by d cube. That's the answer. Now, I want to just change the problem slightly. I will draw Another diagram just to change, not to say overlap and confuse you. I will draw another diagram. Probably everything is same but slightly different. North and south. But the magnet poles I would like to reverse. That is south on the top now, up like not like earlier, north on bottom. Everything is same. Let us consider a point P somewhere in between. I want resultant magnetic induction. Imagine a unit north pole there. So on this unit north pole, due to this north pole repulsion, due to this south pole attraction, this is a resultant of B equatorial 1. Now consider this. On this unit north pole, due to the south pole, this south pole attracts the north pole. This is the direction of resultant force. South pole attracts it. On this unit north pole, this north pole applies a repulsion. So this is the direction of F south. Sorry, this is north, na? F north due to the second magnet. This is the direction of F south due to the second. Because these two forces are in the upper part, their resultant B equatorial will be upward. In this case, B total will be B equatorial 1 minus B equatorial 2, or the difference between them, whoever is higher, resultant will be in this direction. So, I can get a null point. How much is that? Mu naught by 4 pi m by, if I assume both the distances are same, the cube. As the magnets are then, their magnetic moments are also same. I can get a null point, right? So if you want to get a null point, thing that you need to know is opposite poles shall be facing each other. And if you don't want a null point in a problem, similar poles facing each other. I just want you to understand the way that how do you handle directions, because you are handling vectors. That's it. Thank you for watching.